All right, so we are asked to find a power series representation for the function f of x is equal to x squared plus x all over 1 minus x, and also determine the interval of convergence. Now you realize that I can actually write this one as x squared plus x times 1 over 1 minus x all cubed. And once I do that, you could tell that this is something that you've seen before. That's the geometric series, right? So for a problem like this, the idea is to start with a known series, which is the geometric series. So for the function 1 over 1 minus x, the power series representation of that is, so this is n going from 0 to infinity of x to the power n, where x, absolute value of x is less than 1. So here my interval of convergence is between -1 and 1, and my radius of convergence is 1. Okay, so since this power is 3, what we could do is we can differentiate and try to get to this particular point. So we differentiate both sides of this. And once we do that, right, this is 1 minus x to the power -1. So if we do the power rule for differentiation, we're going to get -1, 1 minus x to the power -2 times -1 again, and that's the chain rule, right? So -1, -1, and then this becomes 1 over 1 minus x all squared. So that's what we get for the derivative. Now, when we do that for the power series, you realize that this is again going to be a power rule differentiation, but observe that when n is 0, the very first term is 1. So when we differentiate, that term drops away. So we're going to increase our index by 1. Right, so when we differentiate x to the n, that's nx n minus 1, and it would have the same interval and also radius of convergence. Recall that once we differentiate, the radius of convergence doesn't change. In fact, in this specific case, the interval of convergence doesn't change either. If we test the endpoints and then you realize that both of them would indeed diverge. Okay. So at this step, you'll be tempted to, obviously go ahead and then find another derivative, which will give you 1 over 1 minus x cubed, which is one way of going about it. But another way of thinking about this is to first multiply both sides of this expression here by x, right? So multiply this side by x, and you also multiply this side by x. Now, this side then becomes x over 1 minus x squared, as you can see here. Now, if you multiply this side by x, you're going to get nx n minus 1 times x to the power 1. And so n minus 1 plus 1, that just gives you n x to the power n. And that's exactly what I have down here. Okay. Now, you go ahead and then you differentiate both sides again. So when you differentiate using the quotient rule, you guys will recall for the quotient rule, you're going to have the 1 minus x. You're going to have to square that. And then you're going to have, this is more like u over v. So this is v, so it's going to be v du minus u dv over v squared. And that's exactly what we have here. V is a 1 minus x squared. So you square that. And then v, right, du is just 1. The derivative of x is just 1. And then there's a minus in the middle. But what happens is that if you find the derivative of the 1 minus x squared, right? If you find that derivative, let's just do it here. So we end up with 1 minus x or squared. Okay, so in this case, yeah, so squared. You want to find the derivative, that will give you 2, 1 minus x all to the power 1. And then the chain rule means you're going to multiply this one by negative. So this becomes negative 2, 1 minus x. Remember, you're going to multiply that by u, which is x. So we'll end up with negative 2x, 1 minus x. However, there's already a minus in the middle. So that minus will affect this negative, and that's when it becomes positive. So you're going to get positive 2x, 1 minus x for the u dv portion of it, which if you simplify, you can take out a 1 minus x, right? You can take out a 1 minus x from both of these. And once you do that, on the left-hand side, you're going to be left with a 1 minus x on the left-hand side. So you take out a 1 minus x. On the left-hand side, you're left with a 1 minus x, because there are two of them. On the right-hand side, you're left with plus 2x. Now, 1 minus x plus 2x is just 1 plus x. And so that's how come we have 1 minus x, 1 plus x. And then one of the 1 minus x in the denominator will be cancelled with this 1 minus x. And so you're left with 1 plus x, 1 minus x to the power 3. So this is really, really similar to, what we have there, with the exception of the x. Remember, what we have is x squared plus x. Here we have 1 plus x over 1 minus x cubed. So we'll have to do one more thing to the numerator, and then we're going to get our answer. But remember, when you differentiate this left-hand side, you also have to differentiate the right-hand side. Now here, when n is 1, we have x. So we don't need to change the index because we are not differentiating a constant for the very first term. Because when n is 1, we actually have x. So differentiating this, you're going to get the n multiplying the n, that will give you n squared. And then it will be x to the n minus 1. That's exactly what we have here. So finally, what do we have? So after differentiating, we ended up with 1 minus or 1 plus x all over my 1 minus x, all of that cubed. That is what is given as a sum, and running from 1 to infinity, right? Okay, so let me erase that and do that again. So this is the sum, and running from 1 to infinity of n squared x n to the power n minus 1. Okay, so this is something more like that. All right, so that's exactly what we have here. So finally, you multiply this side by x again, and you multiply this side by x. So once you do that, that gives you the original problem that we began with, or the original one that we want, right? X plus x squared. And then on the right, if you multiply by x and you move the x inside, you're going to get x to the n minus 1 times x to the 1, and that'll give you x to the n. And so that's what we get. So this is going to be our series representation, right, for the function that we began with, which was x plus x squared all over 1 minus x. Okay. All right. Now let's go ahead and then solve for the interval of convergence. So you would recall that in this case, right, my radius of convergence is just going to be 1, right? R is equal to 1. If you want to really think about it, you can use the idea of the ratio test. And so if you use the ratio test, you realize that you're going to have n plus 1, right? So you're looking at a limit as n goes to infinity of n plus 1, all of this one squared, then x to the power n plus 1, all of these under my absolute value, all of I'm gonna have n squared x to the power n. Okay, now what do you see here? The n plus 1 squared over n squared. If you take your limit as n goes to infinity, that's just going to give you 1. Now here is x to the n plus 1, x to the n. And this is going to give you just x. So you end up with this limit giving you absolute value of x. And we know for the geometric series, we need the absolute value of x to be less than 1 for it to be convergent. So in this case, or more or less for the ratio test, when the absolute value of your limit is less than 1, then it does converge. So in this case, your radius of convergence is going to be 1. And at the moment, this is our interval of convergence, -1 less than x, less than 1. But once we differentiate, there is a potential for the endpoints, to have a different convergence, right? So in this case, let's test the endpoints. Okay, so when you differentiate, even though your radius of convergence stays the same, I mean your interval of convergence could be different at the endpoints. And so you want to test those. And so when we take -1 and we put it here, we're going to end up with n going from 1 to infinity of n squared, and then we're going to have -1 to the power. And clearly, this thing would not converge. This one will diverge, right? So it will be alternating, and then you realize that some of them will go to infinity, right? Whenever n is even, and when n is odd, it will go to negative infinity. So this one will diverge using the divergence test, right? It will diverge. Now, if you plug in x equals 1, you're going to have n running from 1 to infinity of n squared, and then 1 to the power n, which is just a sum, n going from 1 to infinity of just n squared. And clearly, this will diverge. If you take the limit as n squared goes to infinity of n squared, this will clearly not go to 0. So this will diverge. And we don't include any of the endpoints. And so this will stay as the interval of convergence. So again, I mean, when you're testing the endpoints, when x is -1, very clearly this will still diverge, by the divergence test, because you won't have if the limit as n goes to infinity of n squared -1 to the n, you won't have a specific limit, right? Because of the fact that it's alternating. Okay, so in that case, it means that it will diverge. Similarly, when n is 1, yes, you're going to get n squared. Use a divergence test and you realize that, you are going to diverge towards infinity. So this here, finally, is my, or this series here is my power series representation of the function that I began with, which is this one right here. And then the interval of convergence is this one. Okay.